So now Hyogo Hiruma will present A3RNN bi-directional fusion of bottom-up and top-down process for developmental visual attention in robotics. So please give him a warm applause.
Okay, thank you for the introduction. I'm Hyogo Hiruma from Waseda University in Japan. And as introduced, today I'd like to talk about A3RNN, which is a visual attention model for robotics. So to start off, this is my motivation about this. Visual perception for robotics is crucial for automating them. So they are used for like observing the environment or detecting target objects, or also recognizing its feedback of its own actions. And to do that, recently, visual attention modules have gained attention, and those modules are a type of models that selectively extract task-relevant vision regions, like the robot itself, and also like objects around it. And these models are known to gain or emerge its attention through imitation of demonstration data, like certain robot tasks. And these are done without giving any explicit labels. And these are known to be done by giving a structure that mimics human cognitive structure. And speaking of human attention, there are generally two types. One is bottom-up attention, and the other is top-down attention. The bottom-up one is the one that is a passive attention, which automatically directs to salient objects, like colors, shapes, and movements. On the other hand, top-down is a active attention, which is the one that directs to certain objects specified by internal or external stimuli. And these two types are known to being used differently based on situations. So bottom-up are used to like search for objects within its visual field, and top-down is used for like precise recognition. And also, these two are known to mutually and compensate each other, so that people can visually recognize things very flexibly in any situations. Given that, in current robotic systems, the ideas of these attention are used for predicting visual recognitions. And they are used, generally they are used quite separately, so bottom-up or top-down, not both of them. So one example about bottom-up is the A3RNN on the left-hand side. And this is the one that extracts coordinates of attention based on the activation that is extracted using convolutional neural networks. And another one of top-down attention is the one that uses temporal feedback of a recurrent neural network, which is a temporal predictor, and use that feedback as a query to determine attention targets. And these two are known to work in a lot of situations, but have some difficulties. And that is, for bottom-up attention, the attention that are acquired or predicted by the bottom-up one tend to flicker spontaneously, so it's quite unstable during inference. On the other hand, the top-down attention does have a quite stable attention, but randomly fails to capture a target during training, so it's unstable during training. So given this, our objective in this research was to propose a new attention model that merges these two different methods to have high stability during both training and also predicting. So to do that, our approach was to combine these two methods directly to make a new attention model. Yeah, so this is our new proposed model, which is A3RNN, which is a short name of amalgamated active attention. And this model uses a framework of imitation learning, which learns to repetitively predict actions of the next time set based on the current observations. So the input is the camera images and the joint angles, shown in red circles, and the outputs are those like the joint angles and the predicted visual image of the next time step, like open 1 second in the future. And this model is composed of three major components, which is A3 model in the green, hierarchical LSTM in the yellow, and reconstruction module in the blue. A3 module is one that is the part that fuses attention queries of bottom-up and top-down attention to generate an amalgamated attention. The HLSTIM is a temporal predictor module which predicts the states of the next time step of bottom-up attention, top-down attention, and also the joint angles. Finally, the reconstruction module is the one that visually predicts the next state of the environment based on attention points, which is a subtask that is used to train this entire model. And as this proposal is mainly focused on this A3 module, I would like to explain this more in detail. So this is the overall structure of the A3 model. The input is the hidden states of the temporal feedback, and also the image features that are extracted using convolutional neural networks. So in abstract, this module is the role of this module is to fuse the bottom-up attention and the top-down attention. And the procedure of this whole entire process is first we extract the bottom-up attention based on the active map of the image features. And after we extract the attention map or the attention map of the bottom-up attention, we generate a pseudo bottom-up query which represents the image features that are included in the attention areas. Next, in parallel, we also generate a top-down query based on the temporal feedback. So once we got the both queries from bottom-up and top-down attention, then we fuse that in, using a transformer block, which has a cross-attention module. And then the resultant amalgamated query is then used to predict the attention points for the final attention output. So that was quite a bit complicated. So a little key takeaway is that this module fuses the two attention types to generate the final attention. And to do that, the fusion was done inside a latent query space instead of a explicit coordinate space, which turned out to be working where the latent space worked better compared to the explicit ones. So given that, we've done an experiment to evaluate this model. The task was a simple box picking task in an environmental RoboSuite simulator using an arm of 7 degrees of freedom Franca Amiga Panda arm. So the training data was collected via teleoperation using a 3D space mouse, and the data we collected was at 3 positions, colored in red circles, and 5 demonstrations per position. And the data was collected in 10 Hz and 120 time step per each. And the modalities we collected, or the data type we collected, was the RGB camera images and the robot joint angles. So the objective here of this experiment was to evaluate confirm the stability of this model during training and also inference times, and also to evaluate or investigate the relation of top-down and bottom-up attention during its developmental process. So this is the results. First of all, the A3RNN had high success rate capturing valid attention points. So in this case, the task was to pick up a box. So the valid attention should direct to the robot arm itself and also the box. As the table shows, we have trained the model for 12 trials. And we, through comparison with the baseline model, which is the original top-down model, the proposed model succeeded 100%, whereas the baseline model succeeded only about 66%. And the videos shown here shows the attention and of the acquired attention. The left-hand side is the proposed one, and about the videos. The left video shows the image and the top-down attention, and the right-hand side video is the bottom-up attention, visualized as an attention map. So as you can see, the proposed model was able to acquire attention of the target box by 100%. And also through analysis, we identified that there were different roles depending on the attention type. So bottom-up had the role of capturing an entire area that had consistent visual changes, whereas the top-down attention were focused more on specific targets that are related to the task. Speaking of the baseline model, it did it did succeed for 66%, but the other 33%, it failed to capture valid attention to the target boxes. And this one is about the analysis of the developmental changes during training. So the figure on the left-hand side shows the change during its development. So the vertical axis, vertical direction, shows the change in time step during inference, and the horizontal axis shows the stage of training. So the left-hand side is the early stage, and the right-hand side is the later stage. And through this, we identified that the development of bottom-up attention showed that in early stages, bottom-up attention had the role of randomly looking at wider areas, which ended up in helping the top-down attention to find the attention target easier. And as the training proceeds, in the middle stages, the bottom-up attention started to look at other places with large visual changes, and in the later area, the bottom-up then attended to the visual areas that are quite important for a top-down attention. So what I want to say here is that target selection had propagated from bottom-up to top-down in the early stages, and then in the later stages, it went back from top-down to the bottom-up. And I think I'm running out of time, so I'd like to go to the conclusion. So generally, I've proposed a model of amalgamated active attention, which fuses top-down and bottom-up. And through evaluation, we identified that this model had high stability during training and inference, and also that through analysis, we found that top-down and bottom-up mutually affected each other during its development of its attention. Yeah, that's it. Thank you very much.
Thank you very much. There's some questions. Yes, up there.
Well, thank you for the talk. I was wondering, because you have a top-down modulation, that if you have tried with distractors of the task, so you suppose that the top-down attention, it should inhibit these objects that are not relevant for the task, while the bottom-up should actually pop it up. I don't know if you have tried with the... So if the task can drive this bottom-up, top-down attention, right?
You're asking about if I've tried with other tasks, or...
No, I'm saying when you are doing a task and the object is a distractor, so it's not relevant for the task, the top-down modulation, what we should observe is that actually inhibits the bottom-up attention part, right? So I don't know if is any possibility to integrate this into your system. I'm not sure I really correctly understand your point, but I think you're asking the top-down attention is the one. In this case, the top-down did in a later part of the training, it did modulate the bottom-up part to see more in the important part of the task instead of just looking at the the parts that had large visual changes. And yeah, so sorry, I didn't get I'm not sure I did get to your point, but okay, I can ask you after.
Yeah, please. Sorry.
Maybe just another one quick question.
Hi, really interesting stuff. I just wanted to, was thinking about how this would integrate from beautiful work from Linda Smith and Chen Yu and others that they presented at ICDLs in the past about the actual real world visual experience of kind of babies and young children when they're learning to reach. One of the things that comes through really strongly from that is that the situation that you've created where it's completely static and there aren't any strong salience cues to reaching is actually something that's actually quite rare in children's visual experience. And they even take it one step further, and they've done some beautiful papers looking at how children manipulate the salience of an object with which they're already cognitively engaged. So they actually, just simply by picking something up and bringing it closer to them, they increase the proportion of kind of edges and motion cues within their field of view. So challenging this whole kind of this whole distinction between top-down and bottom-up.
Yeah, thank you very much. Yes, I think you're very correct. The task I chose this for this research was quite static and easy to use. So in the future work, I would, of course, I would like to integrate this system for not a fixed camera, but also to a head camera that moves along a lot of places and has more dynamic visual changes. Yeah. Thank you very much for the comments.
Thank you. Let's give a warm applause again.